Okay, we're going to have a closer look at ionisation energies. Surprise, surprise, looking at the title there. Now, what did I tell you about ionisation energies last time? We said that as we go across a period, the ionisation energies increases. Okay, it does. It does. However, there are two anomalies that you need to know about. So we're going to talk about those anomalies first of all. Let's just recap though why the ionisation energy increases going across a period. If we go across a period, the number of protons increases. If the number of protons increases, we have a greater nuclear charge. If a greater nuclear charge, we have an increased electrostatic attraction between those protons, those extra protons in the nucleus, and the outer electron. Therefore, more energy is needed to remove that outer electron, because remember the number of shells stays the same. However, it's not a linear trend. Let's plot a little graph first of all. This is going across a period. So let's have a look across our period. So we'll start off with sodium, Na, and then we'll go magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. Okay, so we're going to cross a period here, and on the y-axis we're going to have a scale, and that would obviously be measured in kilojoules per mole, and that will be the first ionisation energy. So I'm just going to write first IE, that stands for ionisation energy, and I'm going to put my units in brackets here as well, kilojoules per mole. Alright. Now, we know that there's a general increase in ionisation energy as we go across a period because the number of protons in the nucleus increases. So our graph goes like that, yeah? So I'm going to put in the points which are consistent with that trend. So sodium, magnesium, aluminium isn't, so let's come back to aluminium, silicon, phosphorus, sulfur isn't, so let's come back to sulfur, chlorine, and argon. Okay, so our anomalies for period 3 are aluminium and sulfur, and these anomalies are lower than expected. So these are lower than expected, these two. And you need to know the reasons for these. It's not the same reason, okay? So you need to know this reason and that reason there, yeah? Let's look at the first reason here, first of all. So this is a group 3 element. Remember, that's group 1, group 2, and group 3. We need to know why the group 3 element is lower than expected. And in doing that, we need to look at the electron arrangements. So we're going to look at the electron arrangements of magnesium and aluminium. So in doing that, we can draw an energy level diagram. So let's draw an energy level diagram for magnesium. So we'll do magnesium here, and we'll do aluminium there. So that's Mg and Al. Remember, Al is our anomaly, okay? So we would have expected that aluminium would have a higher ionisation energy than magnesium, but it's not. It's actually lower. We need to know why that is. And to be honest, it's dead straightforward if you draw the electron arrangements of these particular elements. So if we put on here our electrons, so we've got energy up the side here. I'm not going to write the inner electrons down because they're not important here. It's just the outer electrons that we're going to consider. So we can represent orbitals as boxes, and you can put 2 electrons in a box or 2 electrons in an orbital. And if we say that this is the 3s orbital here, right, 3s. Obviously the 3s orbital in magnesium is going to be the same energy as the 3s orbital in aluminium, or any other element, to be honest. And we've got 3 3p orbitals. Remember, you can only get 2 electrons in each orbital. So if you had an electron arrangement which was, let's say, 3p6, it's not one of these two, but if you had 3p6, then that is not just one orbital. There's 3 orbitals there. So you actually have the 3px, the 3py, and the 3pz. But this is the 3p subshell, so 3 3p orbitals, if you like. Remember the electron arrangement of magnesium? If you write down the shorthand version of the electron arrangement of magnesium, you write neon in square brackets, 3s2. If you write the electron arrangement of aluminium, it's neon in square brackets, 3s2, 3p1. So let's put the electrons in. Remember, you can only put the electrons in the lowest energy first. You can only get 2 electrons in each orbital. So it's 3s2, 1, 2. You see here that the electrons have opposite spin. And 3s2 here again, 1, 2. And then but you can only get 2 electrons in 3s orbital, so we can start a new orbital. So 3p1. Let's stick that electron there. Now, the energy required to remove an electron from an atom is the ionisation energy. So what we've got to do is we've got to remove these electrons, and you quite clearly see here that this 3p electron is easier to remove than the 3s electron because it's already got a higher energy. What we can often do with these plots is we can put like a little dotted line to show when the electron's actually removed from the atom. So we'll like put it up here like this. There. So the energy required to remove a 3s electron is this much energy. Okay, that much. The energy required to remove a 3p electron, however, is only this much. So this 3p electron is easier to remove than a 3s electron. I've just got rid of those numbers there, you don't need the numbers. Let's just keep it simple, P and S. So the P electron is easier to remove in the group 3 element compared to the S electron in the group 2 element. So this electron here is easier to remove than this one here. Now, if it's easier to remove, it means it has a lower ionisation energy. So it's a lower ionisation energy than expected, despite the fact that we've added another proton on. Yeah, this factor must be more important than adding another proton on. So it's easier to remove. So it overrides that particular factor. So that is the reason why you have a little blip in this particular group, from group 2 to group 3. Now, we discussed period 3 here. Now, the question could have quite easily have been period 2. Now, if we look at period 2 on the periodic table, so you've got lithium, and then what is this one? Beryllium, and then boron. You would find a similar drop between beryllium and boron again, because in beryllium you're removing the electron from the 2s orbital, and in boron you're removing the electron from the 2p orbital. So if you were asked in the exam to describe the trend across period 2, it would follow the same pattern. with a blip at these points, but for the same reason. So what I'd like you to do is, I'd like you to describe the trend across period 2, okay, for these as well, in your notes. Let's have a look at this blip here. Now, this is for a different reason. In order to answer this question, what we need to do is, we need to write out the electron arrangement, the full electron arrangement, using box method. So let's compare phosphorus and sulfur. So phosphorus is in group 1, 2, 3, 4, 5, and sulfur is in group 1, 2, 3, 4, 5, 6. So what we're doing here is we're explaining why group 6 has a lower energy, ionization energy than expected. That's what we're doing here. So we're going to write out the electron arrangement of phosphorus and sulfur. Okay, in your notes you should have 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals in each electron arrangement. So I'm going to write down the electron arrangement just normally of phosphorus here, and then I'm going to put the electrons in the boxes, or in the orbitals rather. So we have 1s2, 2s2, 2p6, that's these, 3s2, 3p3. Sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. So let's put the electrons in. Listen to what I'm saying as I'm putting the electrons in, and notice the order that I'm putting them in. 1s2, 2s2, 2p6, right, watch. 1, 2, 3. Remember, I fill them like this because electrons prefer to be in their own orbital. 1, 2, 3, 4, 5, 6. That's a 2p6. 3s1, 2. 3p3. So it's 1. We don't put another one there. 2, 3. Let's do this one. 1s2, 2s2, 2p6. Look at the order that I'm putting them in. 3s2, 3p4. 1, 2, 3. Now, I'm going to have to put my fourth electron in one of these orbitals. It doesn't matter which one I pick. It could be any one of these. They're all equivalent. Let's just put it there. Okay. Now, we're talking about ionization energy here. So ionization energy is the energy required to remove the first electron. So the energy required to move this electron, or this electron. So it's that one, or that one. With these ones though, it is either this electron or that electron. Because these electrons are easier to remove than these ones. The reason why these ones are easier to remove than these ones, and it would go for this one of these ones first, is because, remember, electrons have got a negative charge. If they have a negative charge, they're going to repel. And if they repel, that just makes it a little bit easier to remove from the nucleus. Because remember, all of these electrons are attracted to the nucleus, because the nucleus is full of protons, and it's got that positive charge in there. So remember, we're removing this one, and this one, and they're all equivalent when we're measuring the first ionization energy of phosphorus. And we're removing this one or this one, which is the first ionization energy of sulfur. Now, what we see is, we see a drop in ionization energy from phosphorus to sulfur. And that is because this electron here is easier to remove in sulfur compared to this one or this one or this one in phosphorus. And that's because there's repulsion between electrons in the same orbital. Okay, so the electrons in the sulfur are easier to remove as the electrons are paired in a p orbital. These electrons repel each other, making it slightly easier to remove compared to phosphorus. In phosphorus, in P for phosphorus, the electrons are not paired. So there's no extra repulsion. Okay, so there's no extra repulsion in there. So what you need to do is, in your notes, you need to describe, just like I've done here, for the trend going across period 2. So there's 2 anomalies in period 2, just like there is in period 3. I like to write up period 2 as well. We're now going to look at something called successive ionization energies. And the word successive means to continue. It means more than one. So successive ionization energies. Let's have a look at something like sodium. Okay, so the first ionization energy of sodium would be this. That would be the energy required to do that. The second ionization energy of sodium would be to remove the second electron. So you've already got a singly positive gaseous ion here. And we remove another electron. And the third would be, we take a 2 plus gaseous ion and we remove an electron to make it a 3 plus gaseous ion, and so on. Now, if we have a look here, we can see, if we compare, let's say, the second ionization energy and the third ionization energy. We're removing an electron here, in this process here, we're removing an electron from a positive ion. However, in this process here, we're moving an electron from a 2 plus ion. There's going to be a greater electrostatic attraction between a positive ion and an electron and a 2 positive ion and an electron. So there'll be a greater attraction between a positive ion and an electron compared to a 2 plus and an electron. If you go to the fourth ionization energy, we're removing an electron from a 3 plus ion. So there's going to be an even greater electrostatic attraction between the electron and the 3 plus ion. If there's more attraction, then there's a greater ionization energy. So the general trend is that as we go down the group here, as we go down the ionization energies, go through the successive ionization energies, it becomes more and more difficult to remove an electron. Little sketch here. So we've got IE, ionization energy, and the number of electrons here. Number of electrons. We find that the general trend, I'm not going to put any points in here because it's just the general trend. The general trend is it increases as you take off more and more and more electrons. What I want you to do is I want you to explain that in your notes. Explain in full why the successive ionization is for any element is going to increase. Okay, right. Now, there is a few little blips here. The trend doesn't change like it did here, but there is a few little blips. And it depends on what the element is, and depends on the group of that particular element. We're on the theme here of sodium, so we're going to look at sodium in a little bit more detail. So, let's write down the electron arrangement of sodium, just GCSE style. GCSE style, 2 in the first shell, 8 in the second shell, and 1 in the next shell. Let's count the number of electrons in total. 2 add 8 add 1, that's 11 electrons. So let's draw a little graph for the successive ionisation energy of sodium for these 11 electrons. Let's pick the electrons off one by one. So we've got ionisation energy on the y-axis here. Often we use a logarithmic scale, and that's because it's quite easy to see the pattern of the logarithmic scale. But you don't need to worry about that. We've just got ionisation energy on the y-axis up here. So we've got the number of electrons on the x-axis here. So this is the total number of electrons removed. Okay, so the first electron we know is the easiest electron to remove because we know the successive ionisation energies increase. So the first electron is quite easy to remove. So I'm going to put a little point down here, like that. That's our first electron. That's this one, by the way. Okay, just to let you know. Then what happens is we go into a new shell. So we're finding there's a jump in ionisation energy. And the reason why that is, so the first electron is really easy to remove, and that's because it's shielded by two inner shells. So this electron here is shielded by two inner shells. Shielded by two inner shells. And it's quite far away from the nucleus as well. So it's far away. I'm just adding notes to my graph here. I expect you to write in full sentences when I check your notes. So it's shielded by two inner electrons and it's far away. However, once this electron's gone, the next electron that I'm removing is from this shell here. Now, these electrons are only shielded by this shell. Therefore, those electrons that you're trying to remove feel the nucleus much more strongly. There's a greater electrostatic attraction between those electrons and the nucleus compared to those electrons because they're closer, and they're only shielded by one shell. So there's two reasons there. We still see a general increase here from the second ionisation energy all the way up. Still a general increase, but there is a bit of a jump, okay? So there's a bit of a jump from the first ionisation energy to the second one. And then there's just a steady increase here. So 1, 2, 3, 4, 5, 6, 7, 8 electrons. So I've now removed all those 8. So that's the 9th electron to remove. 1 plus 8 is 9. It's the 9th electron I've removed there. There's a general increase here. So we see there's a jump, right? There's a jump in ionisation energy from group 1 to group 2. You need to describe the jump in your notes. So there's a jump there, and that is because we are now removing this electron here from a new shell. This new shell is only shielded by one inner shell, and it's much closer to the nucleus compared to this electron that you're trying to remove here. There's still a general increase in ionisation energy, and that's because of this reason here, that we've got a 1 plus charge, a 2 plus charge, a 3 plus charge, so we're increasing the electrostatic force of attraction. So you need to explain why still there is an increase in ionisation energy there, steady increase. You need to explain that as well. Once we remove this 9th electron, we've only got 2 electrons left. And again, we're going to have a big jump again. So there's another jump between the 9th and the 10th electron. Yeah. And that's because I'm removing these electrons. Those electrons there are not shielded by anything. So there's no inner shells, and they're really close to the nucleus, so they're going to be really hard to remove. And the last electron is still going to be higher still. Not going to be a massive jump because we're still in the same shell here, but there is still the general trend here where we're increasing the positive charge of the ion. So we'll have a jump between group 1 and 2, between electron 1 and 2, and a jump between electron 9 and 10 as well. So there's a jump there as well. See my question marks? Question mark, question mark, question mark, question mark. I'd like a full explanation around that graph there, why you would expect that one. Okay? And I'd like to do a couple more as well. So the ones I'd like you to do are the successive ionization energies of aluminium. So I'd like to draw the graph of aluminium. And I'd like you to draw the graph of chlorine as well. I'll give you a clue for aluminium. I'm not going to give you a clue for chlorine though. So the clue for aluminium is that there is a jump between the 3rd and the 4th electron. And you explain why there's a jump there. And there's a jump between the 2nd last one and the 3rd last one as well. Just like there's a jump here. Okay. Remember the electron arrangement of aluminium is 2, 8, 3. So you see a jump due to that and a jump due to that. So you need to plot the graph and you need to explain that one. Okay. Chlorine, I'm going to let you plot your own graph, but I'm actually going to give you the data for chlorine. So for chlorine, the first ionization energy of chlorine, if you write this down, is 906 kilojoules per mole. The second one is 1763. The third is 14,855. Beg your pardon, this is not chlorine. And the fourth one, you should be able to see what group it's in though, is 21,000. Can't be chlorine, can it? Can't be in group 7, this one here. But we can't work out what group it's in. And the way you work out what group something's in is you look at the ionization energies and you can see where the big jumps are. So let's ignore all of these numbers here. They're not significant. Let's look at how many hundreds we've got. So this is 900, 1700, 14800, or you could say 14,000 or 15,000, and 210 or 21,000. So we can see here's a big jump between the second and third ionization energy. It's a big jump in ionization energy between the second and third ionization energy. Because there's a big jump in the second and third ionization energy, it means that this must be a group 2 element. If there's a jump there between the second and third ionization energy, it must be in group 2. Similarly, if you had a big jump between the, let's say, 5th and 6th ionization energy, it would be in group 5. If it were chlorine, have a think about where the jump would be, okay, on your graph. If you had a big jump between the 4th and 5th ionization energy, it would be in group 4. So you can look at the trends here, you can look at a graph, or you can look at the raw data and actually determine what group something is actually in. Okay, let's recap this then. So we're having a closer look at the ionization energy. We know that as we go across a period, the ionization energy increases. That's because we're adding more protons. But there are two anomalies. There is an anomaly at group 3 and an anomaly at group 6. The anomaly at group 3 is due to the fact that we're removing a p3 electron rather than an s electron, and a 3p electron is much easier to remove than an s electron. And that pattern is seen in period 2 and period 3. And that's the anomaly at group 3. The next anomaly is at group 6. So we see a drop in ionisation energy, a slight drop in group 6. And that's to do with a paired electron here in a p orbital. Remember, if we've got a paired electron, there's extra repulsion between those two electrons in the same orbital, just making it a little bit easier to remove. Then we looked at successive ionisation energies. You need to know why there's a general increase in successive ionisation energy, and it's to do with the fact that you remove an electron from an increasingly positive charge on the ion, and you've explained that. And then we looked in detail at the little blips here, the little blips between the two shells. So we did sodium, and you would have done aluminium, and you would have done chlorine, and then we looked at data to determine what group something's in as well. Okay.